আজকে তাহলে আমরা ফিজিক্সে ইলেকট্রিসিটি এবং ম্যাগনেটিজমে যে ম্যাগনেটিক প্রপার্টিজ অফ ম্যাটার বা ম্যাগনেটিজমটা আছে সেটা নিয়ে ডিসকাশন করার চেষ্টা করছি। তা আমি কিছুটা স্ক্রিন শেয়ার করব আর কিছুটা মুখে বলবো। সেটা দিয়ে যে কন্টেন্টটা তৈরি হবে সেটা দিয়ে স্টুডেন্টদের আমি একটা গ্লিমস দেওয়ার চেষ্টা করছি। তা প্রথমেই আমি একটা এরকম মিমিও প্যাড ইউজ করব, সেখানে তোমরা দেখতে পাবে। আচ্ছা, শুরুতেই তোমরা জানো যে ছোট থেকে বা আমাদের বিজ্ঞানের শুরুর থেকে যে চুম্বকত্ব বা ম্যাগনেটিজম তোমরা পড়ে এসছো, সেগুলো হচ্ছে সব যে টাইপের মেটেরিয়ালের মধ্যে অ্যারাইজ করে তার মধ্যে আয়রন, নিকেল এবং কোবাল্ট হচ্ছে অন্যতম। আচ্ছা, এর বাইরেও যে সমস্ত পদার্থের মধ্যে ম্যাগনেটিজম অ্যারাইজ করতে পারে সেগুলো এই ক্ষেত্রে নতুন ইন্ট্রোডিউসড হবে, এবং পরবর্তীতে যখন তোমরা সলিড স্টেট ফিজিক্স পড়বে তখন ম্যাগনেটিজম অ্যাজ এ কোয়ান্টাম ফেনোমেনা এর কিছু আলাদা অ্যাপ্লিকেশন হবে। তার আগে এখনো অবধি যে ইলেকট্রিসিটি ম্যাগনেটিজম তোমরা পড়ে এসছো তার মধ্যে থেকে আমি যে এইভাবে ডেভেলপ করার চেষ্টা করছি। তোমরা সকলে জানো যে any matter is composed of atoms consisting of positively charged nuclei and negatively electrons. So if these electrons uh, occur in shells, and the periodic nature of chemical properties of atoms as the atomic weight increases is a reflection of the fact that the chemical behavior of an atom depends largely upon the number of electrons in the outermost shell. The chemical similarity of the rare earth elements, atomic numbers 57 to 71, may be explained on this basis. A similar state of affairs exists in the group of elements of atomic number 26 for iron, 27 for cobalt, and 28 for nickel, all of which contains 2 electrons in their outermost shell, but have 6, 7, or 8 electrons respectively in their next inner shell, where 10 electrons are required to fill the state. So, as a consequence of the electrons in the unfilled shell of one atom may exert an important influence on the electrons of the unfilled shell of a properly spaced adjacent atoms in a crystal. The ferromagnetism of iron, nickel, and cobalt is explicable in terms of the electronic configuration of these partially filled shells. The magnetic properties of matter arise from two sources. Very importantly, an electron in orbital motion above the nucleus constitutes a small circulating current which generates a magnetic field, and the electron moving in its orbit has an angular momentum about the nucleus, that is one is angular momentum of the electron, another is about the nucleus. In addition to the magnetism due to its orbital motion, an electron has its intrinsic angular momentum owing to its spin. We know that electron is a spin half particle having plus half or minus half spin depending upon the direction of the spin. So in the absence of the magnetic field, the orbital magnetic moments and the intrinsic magnetic moments of different electrons are randomly oriented within the matter. There may be relatively a large local magnetic fields in small regions, but when these magnetic fields are averaged over a volume of even a cubic millimeter, the average field is zero, so that macroscopically no magnetism is displayed. Most materials are only very slightly magnetic in the presence of external magnetic fields. They are said to be either diamagnetic, the new term introduced, either diamagnetic or paramagnetic, right? Uh, so a diamagnetic material is one for which Km, my relative Km, is less than 1, and for dia and for paramagnetic, this Km is greater than 1. Uh, so in case of dia, the magnetic effects induced in the material are opposed to the external field. We would expect materials to be diamagnetic if the orbital electronic effect predominated for in accordance with the Lenz's law, and the magnetic effects induced in a circuit must be in such a direction as to oppose the change in magnetic field in the substance. Paramagnetic material is one for which Km is greater than 1. I already have said. When placed in a non-uniform field, a diamagnetic substance will experience a force directed from the stronger to the weaker part of the field. A paramagnetic substance will experience a force in the opposite direction. In general, in all materials except those called ferromagnetic, that is those which behave like iron, the magnetic effects are quite small, and these materials may be treated as though their relative permeability Km is 1 to an accuracy of about 0.1%. The magnetic behavior of most substances is not substantially different from vacuum. A ferromagnetic substance is attracted into a magnetic field with a large force. The relative permeability K of a ferromagnetic substance may be as large as 10 to the power 4 to 10 to the power 5 km for ferromagnetic substance. Ferromagnetic substances are therefore special cases of the general class of paramagnetic substances. The subject of ferromagnetism is of great importance in electrical engineering and is complex as it is important. The properties of ferromagnetic substance form the basis of the practical design of motors, generators, transformers, magnetic amplifiers, tape recorders, loudspeakers, permanent magnets, and host of their devices. We shall attempt to develop only some of the basic ideas of ferromagnetism and to solve problems to the simplest type in which the symmetry considerations enable us to see the important principles most clearly without the confusion of details which cannot be neglected in practical engineering design. So as we all know, we start with H equals to 0, the basic thing, the magnetic intensity H equals to 0, and the unmagnetized iron in which the magnetization M is 0. And then B, my B is equals to mu 0 H plus M, that is the equation for magnetic induction within the coil is 0 initially. By measuring the successive changes in B as in H varies, we get a series of values of B. Uh, in case of say magnetization, what kind of curve is being obtained for this? If this H is in Orsted and my y-axis is the B, the uh, magnetic field in Gauss or Tesla Gauss, the kind of nature is initially begins from 0 and then reaches in A like this. This is the magnetization curve of the soft iron, right? So what happens? Uh, the magnetic induction B, increases slowly at first with increasing age, then increases more rapidly in this region until the flat portion of the curve reaches at A. So along the flat portion of the curve, the iron is said to be saturated. Very little further magnetization in the iron is observed when H is increased, and the increase in B is due to the increase in H itself. The curve appears flat because of the difference in the scales used for B and H. The relative permeability Km may be defined or obtained from such a curve, and the relationship B is equals to Km mu 0 times h when the scales of the axis are represented in mks units. The shape of the curve and the permeability itself depend upon the types of iron used. In some laboratory examples of iron, a relative permeability as high as uh, this thing uh, can be as high as 10 to the power 6, as I already mentioned for ferromagnetic materials, has been achieved. So in terms of this, I next discuss what is that is what is hysteresis or so. Sorry, uh, in the next page, very important phenomena the ferromagnetic material exhibit, that is hysteresis, right? So let us take a piece of unmagnetized iron in the form of ring of circular cross section, wind a toroid around it, then wind a secondary coil around it, and connect it to a battery and meters. Uh, if we send current through the coil and magnetize the iron until the magnetic induction has reached its saturation value, the kind of plots it can show, if this x-axis is magnetic intensity and this is origin, my curve like goes like this uh, up to A, then it returns back like this, and this is the complete curve. If this is D and this is C, this is my y-axis, like B, the magnetic field. So as shown in the figure, the variation of B with H follows the magnetization curve OA, this increase in the magnetic field. If we now decrease the current in a small steps, if we decrease by this, it is found that the demagnetization curve does not follow the original curve OA, but instead follows the curve AC. AC, the value of the magnetic induction remaining when the current in the toroid is reduced to zero by OC. The iron is now permanently magnetized. So if you can easily see that when my magnetic intensity vector is zero, there is a magnetic field inside the material. So this is very important. This iron, the iron is now permanently magnetized, and the value of the induction OC, mm, the value of the induction OC is called the retentivity, right? Sorry, the value of the magnetic field is called retentivity, right? This OC is called the retentivity because in absence of the field, there has been a uh, there has been a permanent effect of the magnetization. So in permanent magnets, a high retentivity is required, while in other applications a low value of the retentivity is required. To reduce the magnetic induction to zero, that is to demagnetize the iron, it is necessary to reverse the current in like this very important phenomena. uh, if this is my axis and the curve begins like this, then when return back it looks like this, have the value this, and it returns back like this. So if my this axis is H, this is the B axis, so it starts from O, mm, goes to A saturated, and then demagnetization effect AC follows D, where my uh, magnetization is zero, and this is E, this is F. So my magnetic coil is under to reverse the direction of the H. When H has reached the negative value given by OD, this value is OD, the induction within the iron is reduced to zero. The value of H needed to reduce B to zero is called the coercive force. Coercive force. The fact that B lags behind its previous value while H returns to its former value is called hysteresis. This irreversibility nature in the ferromagnetic substance is typically called hysteresis. All ferromagnetic materials exhibit the phenomena of hysteresis. One of the effects of hysteresis is that the value of B for any given value of H is not always the same, but rather depends upon the magnetic history of the material. If an alternating current is sent through the toroid wound on a ferromagnetic core, the BH curve will be similar to this curve, right? Hysteresis loop in the cycle of magnetization of iron. So from the energy per unit volume in the magnetic field depends upon the product BH. While the iron is being magnetized, energy is being stored in the magnetic field. When the iron is demagnetized, some of the energy is recovered as electrical energy. In traversing one cycle of the hysteresis loop, the energy per unit volume of iron dissipated as heat as the area inside the hysteresis loop. In the design of AC machinery, it is important to that a type of iron be used in which the area enclosed within the hysteresis loop is small, so that a minimum of energy is lost through this mechanism. A simple way of demagnetizing a substance is to place it inside a coil and pass alternating current through the coil. The amplitude of the alternating current is decreased slowly so that the hysteresis loop gets smaller and smaller in successive cycles, right? So, like in this case, if we plot this, so we are discussing the magnetism or magnetic properties of matter. So in case of this, I have already discussed the earlier slides, so I can screen share, and in the Mimeo pad, I will discuss the rest, right? So if this is my axis, and this is H, and this is B, and my loops are being like this, right? I am taking some other color so that the coercive field as well as the retentivity decreases like this, and some different color. This look like this, and for some other color, the loop like this, right? So this is the typical hysteresis curves obtained by using alternating current of successively small values of primary currents, right? So in case of mm, uh, as we discussed that the amplitude of the alternating current is decreased slowly so that the hysteresis loop gets smaller and smaller in successive cycles as shown in the figure. So until finally when the current in the coil is zero, the values of B and H are zero, right? So the hysteresis loop is explained by means of domain theory of magnetism. That is the most important theory, domain theory of Magnetization. Domain theory of magnetization, which was first proposed by Wise, P. Wise. According to this theory, a ferromagnetic material is composed of many small regions or domains, each magnetized to saturation and about 5 into 10 to the power minus 3 centimeter in width. When a suspended of colloidal magnetite is applied to a highly polished piece of iron, while it is being magnetized, the colloidal particles collect near the domain boundaries and may be observed with a microscope. So this kind of phenomena are being observed. If this is my, I am figuring the domains for this. I have to plot like that. And these are my domains. These are my domains, and here my spins are like that, here like that, here like that, like this, like that, like this, like these, like these, like that, and these, and this. And this is the typical diagram for the interpretation of the domains, right? So when the suspension in the unmagnetized state, the directions in which the domains are magnetized are distributed at random or in some other way such that the resultant magnetization of the specimen is zero. Changes in the total magnetization of the specimen are produced by changes in the direction of magnetization of the domains or by motion of the boundaries of the walls of the domains. Uh, so typically it looks like this. And some other orientation it looks like that. In other orientation it looks like this. Right. This is the magnetic intensity. So original magnetization of two adjacent domains, that is in the figure A. In the figure B, change in magnetization as a result of the growth of one domain at the expense of the other, that is in B, and change in magnetization resulting from a change in the direction of magnetization within the domains, that is plotted as C. So at weak fields, the magnetization proceeds by boundary displacement. When the material is very pure and homogeneous, the boundaries of the domains are easily changed, and so the coercive force is small and the permeability is high. When impurities are present or the material is in a state of internal stress, the material is inhomogeneous so that the boundaries of the domains are less easily displaced. The initial permeability is lowered and the coercive force is increased. By sintering a magnetic material of very fine powders or by precipitating an impurity or another metallurgical phase, the displacement of domain boundaries is hindered and good permanent magnets are made, which require a large demand magnetization field to alter their magnetization. At high magnetic fields, the magnetization is accomplished by rotation of the direction of the magnetization within the domains. When the direction of magnetization in all of the domains is parallel to the applied magnetic field, the material is saturated. So the motion of the boundary walls of the magnetic domains does not occur smoothly, particularly along the steep portion of the magnetization curve. This irregular motion produces sudden changes in the magnetization of the specimen as the magnetizing force H is changed. If the galvanometer is in the secondary circuit is replaced by the amplifier and loudspeaker, a successive of clicks will be heard when the magnetization is changing. This effect is known as Barkhausen effect and was discovered by himself. So from the hysteresis figure, we can point out that from this figure, particularly, we see that the magnetization which remains in a specimen when the applied magnetic field intensity is reduced to zero depends upon the magnitude of the applied field, and through the residual magnetization the specimen remembers the amplitude of the applied field. The magnetic memory is the basis of magnetic tape recorders and of many present day electronic computers. When a specimen is magnetized, it behaves as though there were magnetic poles at the boundaries of the specimen. If there is a crack in the specimen, poles of opposite polarity appear on the adjacent faces of the crack. This is the basis of the magnetic inspection of ferrous machine parts, widely used in the aircraft maintenance of the production. So in a way, if we introduce another quantity, uh, the magnetic properties of solids are described quantitatively in terms of the magnetization M, which is defined as the magnetic moment per unit volume. My magnetization is like that. Sorry. My magnetization, which is defined as the magnetic moment per unit volume. So most solids are only weakly magnetic and develop a magnetization only when an external magnetic field is applied. In such cases, the amount of magnetization that is developed depends upon the magnitude of the magnetic susceptibility, which is defined as chi times H, right? This chi is very important quantity. This chi is in general a tensor in a crystalline solid. In Gaussian units, chi is dimensionless since m and h are both measured in the same units, that is Gauss. So materials for which chi greater than 0 are denoted as paramagnetic, and chi less than 0 are diamagnetic. Materials with a spontaneous polarization, that is, which exhibit a magnetization M without application of magnetic field, typically have much larger values for chi and can be either ferromagnetic, ferro, or antiferro, or ferri. Can be of these three: ferromagnetic, antiferromagnetic, and ferrimagnetic. We will discuss later on. In the present chapter, we focus on the materials which are either diamagnetic or paramagnetic and do not exhibit spontaneous polarization. So magnetic moments in solids can be associated with both the conduction electrons and the ions, or closed shell valence electrons. In the case of electrons, magnetic moments are associated both with the orbital motion and the spin angular momentum of these electrons. To understand the intimate connection between magnetic moments and angular momenta, we review here a few basic definitions. In CGS units, the magnetic induction B is related to the magnetic field H through the permeability mu, that is mu H, that is h plus 4 pi m, that is h plus 4 pi chi dot h, that is 1 plus 4 pi chi times h. So my mu is equals to 1 plus 4 pi chi, that is greater or equals to 0, where 1 is the unit second rank tensor having 1s along the main diagonal and 0 elsewhere. The condition 1 plus 4 pi chi is greater or equals to 0 is required by thermodynamic stability, so that the maximum diamagnetic susceptibility is chi is equals to 1 upon 4 pi, which is the value of chi for superconductor and has complete exclusion of the magnetic field. B is equals to 0. Another important fact, the magnetic moment associated with the angular momenta is mu is equals to E upon 2mc times L. L is the angular momenta, in which angular momentum for electrons in atomic states is quantized in units of h cut, and therefore the magnetic moment is quantized in terms of Bohr magnetons, that is mu b. Mu b is equals to E h cut over 2mc. The value of typical of this 0.923 into 10 to the power minus 20 arcs per Gauss. The charged particles of solids, electrons and nuclei not only have orbital angular momentum, but can also have spin angular momentum s. Magnetic moment mu is also associated with the spin angular momenta s, and the experimental studies of atomic spectra show that the magnetic moment associated with the electron spin can be related to s by this. Mu is equals to E gs divided by 2mc times s, where gs is the Landesi factor, for which is 2 for free electrons, and since E is a negative number, the magnetic moment and spin are anti-parallel. So I am terminating the course here, and maybe few questions can be entertained, right? So I am terminating